Hello, my name is Sam Kurtzinger, and this is Lab 2, Motion of a Falling Object. First, I'm going to show you a recording of my friend Andy dropping a computer case. Next, we will analyze the movement of the case in a program called Tracker. And then we will use VPython to create a model of the object as it falls. Finally, we will compare the experimental data with the models generated from VPython. You will see that by calculating the force of gravity and the drag force and applying them to Newton's second law, we can accurately calculate the motion of a falling object. Here is the original video of Andy dropping the computer case. Once the video has been loaded into Tracker and the object's motion has been tracked, it becomes clear that the object is accelerating and therefore the net force on the object is non-zero. The coordinate system is based at the case's initial position. You can see as the case falls, it moves in the negative y direction. The fundamental principles on this slide mathematically explain the motion we see happening in the video. The first equation, Newton's second law, relates the final velocity of an object to the object's previous velocity by adding the quotient of the net force in the object's mass times the change in time. Unlike Lab 1, which had a net force of 0, Lab 2 has a non-zero net force. Furthermore, there are multiple forces on the object. These two forces are gravity and drag. Gravity, which is represented by Fg on this slide, is calculated as the product of the object's mass and Earth's gravitational acceleration, 9.8 meters per second. To calculate drag, we chose to use turbulent drag rather than viscous drag, as turbulent drag is more accurate in this case. We represent it by Fd on this slide, and you can see it is b times the square magnitude of the velocity. B was calculated through empirical methods. It is important to note in this drag formula that as velocity increases, drag increases exponentially. The net force is modeled by the sum of the force of gravity and the drag force. The final equation on this slide is the change in position formula. It's represented by the object's initial position plus the product of the average velocity and the change in time. This slide simply helps to show how the physics translates into code. Ball.m represents the ball's mass. J hat is the vector pointing the direction of the drag force. G equals the Earth's gravitational constant. Fg represents the equation that calculates the force of gravity. Fd represents the equation that calculates the force of drag. Fnet is the sum of the two. Ball.vel represents Newton's second law, and ball.pos is the change in position. Here are screenshots of my code. You can pause the video if you want to read them. Now I will show you the code running. Observe how our fundamental principles in our video align with this model. The object accelerates downward until the drag force is great enough to equalize the force of gravity to bring the object to a constant velocity. This constant velocity is represented by the line straightening out on the graph to the right. Here is a plot of all three data sets. The blue dots are the data points calculated from the video and Tracker, our experimental data. The orange line is the Python model that accounts only for gravity, not the force of drag. And the red line represents the Python model that accounts for both gravity and the drag force. The alignment of the blue experimental data and the red data produced from the model proves that when we account for both gravity and drag, Newton's second law is an accurate prediction of the motion of a falling object. This concludes thoughts on our data, and now we will move on to the what-if questions. Which model might predict terminal velocity? The model that accounts for drag predicts terminal velocity. This terminal velocity occurs when the drag force equals the force of gravity. The model that neglects drag allows the object to accelerate indefinitely. What if we threw the object downward? Let's use VPython to simulate this unique situation. The first plot is a model of an object being dropped with an initial velocity of 0. The second is a model with initial velocity of negative 15 meters per second in the y direction. In the first plot, the object accelerates until the drag force equalizes with gravity. The second plot is the opposite. The drag force is greater than the force of gravity, so the object has to slow down until the drag force equals that of gravity. Regardless, they still end in the same terminal velocity. This concludes Lab 2. Thanks for watching.